First of all, the mathematical object is a fractal, and you can zoom infinitely deep into it and always see new complex structures. It is also self-similar to some degree, which means that deep inside it you can find structures that...
Oh, come on! Should I blow my speaks?
At least the graphics are cool.
Oh man. I'm really sorry. Sorry.
I can hear it. It's fine.
Anyone hear it?
I think it's this. It's not your speaker.
The outfit. This is a thing called the. This is a thing called a Julia set. Oh, I turned these off. Thank you.
f of z is equal to z squared plus c, where c is some complex number.
These are
If
Julia
the fate of
sets.
the complex number is such that it escapes to infinity, we color that complex number based on how quickly it escapes. And if the number gets stuck and stays bounded, we just color it black. Recall also that the only thing that is different in all of these images is simply that constant number c that we are adding on top of the squaring. So every single Julia set corresponds uniquely to some complex number, and since there are infinitely many complex numbers that we could be adding, there are also infinitely many Julia sets. Now, as mathematicians were looking at these examples of the Julia sets, they noticed that there are basically two easily distinguishable groups that every single Julia set falls in. Simply put, we have a group of Julia sets that contains black regions of complex numbers that stay bounded. And then we have a second group of Julia sets where we cannot see any such regions, and almost every single complex number escapes to infinity. We call all the Julia sets in the first group to be connected Julia sets, because all the black points are connected together and they form a region. The other Julia sets are called disconnected, because while there may still be points that are black, these points are always spread out and never form a region. But mathematicians were not satisfied with such an imprecise rule for classifying the Julia sets. Finding black regions is very hard, and in some cases it may be very hard to tell if the image contains a black region or not. So they went ahead and they proved a very important theorem that can give us a quick way to tell the connected Julia sets apart from the disconnected Julia sets. It turns out that you only have to look at the fate of 0. You look smack in the middle of a Julia set, right here where 0 is located. If 0 stays bounded, the Julia set will be connected. And if 0 escapes to infinity, the Julia set will be disconnected. Notice that this is a very bold claim. I mean, can you really not have a Julia set where you have some black region somewhere off the side in here, and everything else, including 0, escapes? Well, no, in fact, you can't. The full mathematical proof is too technical for our purposes. But look at all these examples to gain a little bit of trust in this statement. So 0 is right here. Notice how every time the Julia set contains some black regions, 0 is always a part of that black region. In other words, asking whether or not a Julia set is connected or disconnected is the exact same thing as asking whether or not 0 stays bounded or escapes to infinity. So this is wonderful. You can now give me any complex number c, and I can tell you right away if the corresponding Julia set is connected or not. The way I'm going to do this is that I will simply check if 0 stays bounded or if it escapes to infinity, as it is repeatedly mapped under the function f of z is equal to z squared plus c. So let's say you want to know if the Julia set corresponding to, for example, 0.4 plus 0.1i is connected or not. Now, I know that to answer your question, I only have to look at the fate of 0. Does 0 escape to infinity, or does it stay bounded? So I start with 0 and apply my function to it. So 0 squared plus 0.4 plus 0.1i, I get 0.4 plus 0.1i. I square what I got, and I add 0.4 plus 0.1i. I square what I got, and I add 0.4 plus 0.1i, and I continue in this fashion. Now, in this particular case, it looks like 0 will escape. So I will make the educated guess that if you were to look at all the other points and generate the entire Julia set, it will be disconnected. And I would be right. Here's the image of the entire Julia set. So 0 is somewhere here, and you can see the path that 0 followed. It looks like it first goes to the right, and then snaps down and escapes. And you can see that the Julia set is disconnected, and almost all of the other points escape with 0 as well, in all kinds of other crazy ways. And now comes the crucial part. apart. We saw that Julia sets corresponding to some complex numbers are connected, and Julia sets corresponding to other complex numbers are disconnected. And we would really like to see these points graphically, so we will make another diagram to visualize the relationship. We will again have the real axis going to the right and the imaginary axis going up. Points in this plane will correspond to all possible C values that we would like to look at. And for each possible complex number C, we will ask whether or not the Julia set corresponding to that number is connected or not. If the corresponding Julia set is connected, in other words, 0 stays bounded for that C value, we will color that number black. And if the corresponding Julia set is disconnected and 0 escapes for that C value, then we will color that number based on how quickly 0 escaped. So 0.4 plus 0.1i is somewhere here. 0.4 across real and 0.1i. And we saw that if C is 0.4 plus 0.1i, the resulting Julia set is disconnected because 0 escaped. So let's color this number based on how quickly 0 escaped, say some blue color. And now just do the exact same thing for all the complex numbers in this diagram, one by one. Exactly which C values give rise to a connected Julia set? What do you get? I'm guessing that some of you may have already guessed the answer. Indeed, what you get is a celebrated Mandelbrot set. And our friend 0.4 plus 0.9 is somewhere here, colored blue. And in fact, this program called Fractal Extreme lets you explore all the possible Julia sets. I am moving my mouse cursor around the Mandelbrot set on the left, picking C values. And the program draws the corresponding Julia set on the right. As expected, when I move my mouse cursor around the dark regions, we get the connected Julia sets, including our very old friend, the boring circle, one of the first Julia sets that I introduced you to. Somewhere here, corresponding to the value C equals 0. Similarly, when I move my mouse cursor outside, we get all the disconnected Julia sets, including our friend 0.4 plus 0.1i somewhere here. So this program, by the way, is free, and I encourage you to download it. I will post the link into the video description.
It's on your little program.
And play around with it because it's a lot of fun to explore the universe of the Julia sets. And you can, of course, zoom in here or here and explore everything in much more detail. Finally, I would like to show you one more interesting picture that shows the approximate shape of the Julia sets for all different C values. It gives a kind of an overview. Again, notice that all the connected Julia sets are lying inside the big black region of the Mandelbrot set. And that concludes the video. Thank you for watching, and I'll see you later.
That's cool. I think that was a cool video. I learned a lot from that thing. So that concludes my talk for the most part. Like I say, if there's any questions you have about the things that are on this program, let me know. And the URLs for the Fractal Extreme program that he was referring to, as well as that video, are on there. There's some other kind of funky, cool, like music videos that have to do with the Mandelbrot set. One of which I almost included, but I just thought it would be too goofy. So yeah, hurry.
I brought a calendar down.
Cool.
That all of the artwork in this calendar was generated using formulas much like the Mandelbrot set was in the formula is down here at the bottom for each one of the pictures. And so if you want to take a look at it, you can. But I'll just leave it here on the table for a while. It's pretty cool.
And you can find those calendars all the time. So anyway, thank you very much for coming.